Hello, thank you very much for coming after school. So I am going to try and talk you through all of these syllabuses in the time that we've got. So it's going to be quite a whistle-stop tour, so hopefully I can take you with me as we go. And what I'm going to focus on is trying to show you the differences between the syllabus you are familiar with and the syllabuses we now have. So focusing very much on that as the thing, and also thinking about the philosophy of Cambridge within that and how Bill and various other writers have put things together. So we're going to start off with Standard 2, and with Standard 2 I've very much focused on where the content has come from the previous syllabus, the General 2 syllabus. So I'm looking here and saying we start off with algebra. Now you may be aware that the way the syllabus is now split up is you have broad brush strokes of topics, so algebra, measurement and so on, and then within those you have subtopics. So it's just the way of arranging the syllabus. And if we look at algebra, types of relationships in Year 12 Standard 2, where that's come from is it's come from the AM2 part of Year 11 General 2, and it's also come from it's come from Year 11 General and also from Year 12 General 2. So if you're looking to try and find some material on that to make your programming easier, it might be good to just go back and look at those. What has changed is this stronger emphasis that they talk about a lot on application and modelling. You may have noticed within the syllabus you have this AAM that's written throughout the syllabus in various points. That was originally there to indicate where the focus studies had gone once the decision was made to move the focus studies within the topics. And then it's sort of like, well, here's another idea that would be a really good application. Here's another idea. So it's not limited to the focus studies, but it is where those focus studies have gone. And so we're looking at trying to emphasise where will this be used a lot more. The questions may be a bit more about application, not just about do this. Measurement non-right angled triangles, the sine rule, the cos rule, and so on, that's come from a combination of these two areas. And then rates and ratios, and here's a good example of where the focus studies have sort of been integrated within those particular topics. So Year 11 General is where some of the basic stuff on rates and ratios is, and then the applications of those comes from this focus study and from this focus study. So for example, things like house plans, it's come from there. And again, if you go back programming-wise and look at what you had in those areas, that might be a useful thing to then bring across. We've then got finance. Now, finance and statistics, the two on this page, is where we have a lot of what they are now calling common content. So you may be aware that there is common content now between Standard 2 and the advanced syllabus. The idea of this being that you can collect some data from when they sit their HSC and give that to UAC to try and sort out the scaling problem that we've had for a number of years in terms of the fact that, you know, which course do we do and let's play the scaling system. So to try and eradicate that problem shouldn't affect the actual HSC itself. There is this common content. So the common content is indicated in the syllabus by little paperclip symbols where NESA feels that there is common content, and they've also produced a document that lists where they feel the common content is. There are some bits that are back here, little drop-fed bits, and we'll talk about those a bit as we come to the advanced syllabus. But the big bits are in the finance area and in the statistics area is where you'll find quite a lot of that common content. And if we look at finance, so we've got the basic sort of finance of your compound interest and looking at these things, focus more on the application. So it actually says as a dot point comparing different investment strategies, which wasn't there before. I could see that being a good alternative assessment, perhaps getting them, you know, here's one way of doing it, here's another way of doing it, let's try those different ways, maybe. And then with the annuities, you've actually got, again in the syllabus, sometimes them saying not using technology or otherwise, but just using technology. So very much specifying you are going to be using technology at this point. How they're going to assess that, I'm not sure. I don't know if they have any thoughts on that. A couple of ideas that occur is that you want to do that in your classroom with the alternative assessment. Perhaps it might get to the point where you take a screenshot of something done in technology, a spreadsheet, and then you're asked questions about that. I don't know. But I do think that we need to try and do a little bit of this using technology within what we're doing in the classroom, if we don't already. We've then got bivariate data analysis. So that is when we start to look back to stage 5 and think, okay, so actually there is bivariate data analysis in stage 5. It's there in stage 5.3. So not necessarily the students that are going on to do the standard 2, but maybe we need to have another look at that programme and lead them into this a bit more than we are. So we might do a bit of rearranging at the stage 5 level. And I'll talk about that a little bit more when we get on to advanced as well, about the implications for stage 5 and below. A lot of this was there in this area, but the extra bits, we've got Pearson's correlation coefficient and a bit more of an emphasis on interpolation and extrapolation. It was sort of there before, but it wasn't specified in a dot point in the syllabus in the way it is now, about you need to know when is this appropriate, when is this appropriate, and actually analysing that a bit more. All the Z scores and the normal distribution was there in this here, General 2, but what we've now got is 2 extra dot points at the bottom. In fact, if you look, it's pretty much the old stuff moved across, but with 2 dot points added at the bottom about use the Z score to do this and use it to do this, and it's to do with how you use it to make judgments about situations. So that's your Year 12 Standard 2 in a nutshell. So you've got your algebra, measurement, finance, statistics, and then this, which is new for everybody. So we've got this networks topic. And I thought I'd just spend 5 minutes going through a couple of bits about this. I don't know, how many people have done networks at all, ever? Okay, good. So it's new for a lot of people, so you really need to try and familiarise yourself with a lot of the terminology and what's going on. It's not as difficult as it might seem. And what I'm going to do here is I'm going to talk through some of this terminology very briefly. It is terminology heavy, which is a worry when we're talking about Standard 2 students, isn't it? Because they are not going to be the most literary students in the world. So it's something that we need to handle very carefully and make sure that we've got appropriate books, resources that set us up for learning this terminology. But look, over here I've got a network. Here's a network on the board. And what it does is it indicates links between things, whatever those things might be. So here's some things and here's some links between things. And then I can talk about it in quite an abstract way. So if I want to walk around this, I want to do a walk around this network, that's basically just any way of travelling around the network. So I start from a point and I just travel around. I might repeat some edges, I might repeat some vertices, I might go around the same bit twice. Any way of travelling around that network is called a walk. And if I put letters on all the vertices, then I could list the walk and say I go A, B, C, D, E, C, E, D, F, and the order in which I'd travel through those vertices. A trail is then a walk which doesn't pass on the same edge twice. So I can go round here. I could pass through the same vertex twice, but I can't pass the same edge twice. I could have ones that are closed. So a closed trail might be one like I just did there, and I finish where I started. So it can be closed or not closed. Trail, not the same edge twice. Then a path is not the same vertex twice. So a path, I couldn't do what I just did there where I went like that. A path, I'd just have to go around pretty much in a loop. And that's what becomes important when we come on to the algorithms that it asks you to deal with later, because we want to avoid closed paths, or what we also call cycles. So a cycle is basically a loop of some description. That's a cycle, not repeating itself in the terms of any edges or vertices, but just going round in a loop. And I don't like cycles when it comes to what I'm going to do next, which is looking at trees. So we have trees. This up here is a tree. This is not a tree because look, there's a cycle. So this is a tree because it links all those vertices together. I could travel from any vertex on this tree to any other vertex on that tree somehow. I could get from there to there. Here I could too, but here I've got a cycle and I don't want cycles. So a spanning tree is a tree that uses all the original vertices from this network. So if I had this network and I wanted a spanning tree of this network, I'd need to rub out some of these edges. So I might get rid of this edge, maybe this one, and I need to get rid of enough edges that I'm just left with a tree. So I've still got a cycle, so let's get rid of that cycle there. Let's get rid of that cycle there. This is still a cycle, so I'll get rid of that. And now I've got a tree. So I could still get from every point on the network to any other point on the network, but I haven't got any cycles. And that is a spanning tree of the original network. So then we have a minimum spanning tree, which is what the syllabus talks about. And a minimum spanning tree is I need to have weights on the edges to be able to do a minimum spanning tree. So numbers put on these edges. And they could represent any number of things. They could represent how long does it take me to get from there to there. It could represent the distance of how far it is from there to there. It could represent the cost of laying the road from there to there. It could represent the cost of the cable, how much data flows, how much water flows. It could represent any number of things. It'll be specified in the question. And what I want with a minimum spanning tree is how do I join all the vertices together for minimum value? Quite often, a sort of example would be connecting lots of different things with computer cables, for example, supposing we don't have a Wi-Fi option, for minimum cost, for example. How do I connect the plumbing up, where all I want is or electricity? I just want everything connected to everything else in the minimum possible way. And there are algorithms for doing that. There are two of them. There's Kruskal's and there's Prim's. They're both greedy algorithms. The syllabus doesn't talk about greedy algorithms. I don't know why, but that's what they are. They are greedy algorithms because they make the immediate decision for the next step. What's the best decision to make right now without considering the big picture? So the situation I'm in now, what's the best thing to do next? Which we know, if you think about proofs and things like that, it's not always the best way to go, is it, to go directly there? Sometimes you need to go around here to make it more efficient long term. But these are greedy algorithms, and that's what they do. And I'm going to talk you through very quickly through Kruskal's algorithm to show you that it's not as hard as you think it is. So it sounds horrible. Here's Kruskal's algorithm, and here's how we explain it. We're going to choose from those edges remaining an edge of least weight, which doesn't form a cycle, rah, rah, rah. And I'm going to do this until I've got n minus 1 edges. So there are n vertices, so I've got 6 vertices. And if I want a spanning tree, I therefore need 5 edges, because 6 vertices, 5 edges. Or I just keep going until I've got all the vertices, whichever way you want to think about it. So I need to know all the edges in order of weight. Here they are. And let's look at actually doing it then. So here is my diagram. Which is the shortest edge, or the smallest edge, or whatever you want to call it, the edge of least weight? It's that one. So that's the first thing I put down. The next one is the 3, df, so I put that down. Next one, I've got 2 options. I've got a 4 that's here, and I've got a 4 that's here, but I don't want that one because that would make a cycle. And I don't want a cycle, so I don't want that one, so I want this one. Then I've got 2 options for 6, that one or that one. Neither of them make a cycle, so I can just choose one arbitrarily. I'm going to choose that one. But that means I now can't choose the other one because that would make a cycle. And then finally, 7 is the next one. I don't want to choose this 7 here because that would make a cycle, so I choose that 7. And I've now got all the vertices, and that's my minimum spanning tree. The problem now becomes, what is NESA expecting to see in an HSC exam in terms of workings for this? Don't know. I'll make a guess. A guess would be, okay, what can I get the students to do that's fairly straightforward? I can get them to write the edges in order of size. Okay, I can get them to do that, that's fine. And then I can go through and say, right, okay, tick, tick, no, I don't want that one. Tick, tick, don't want that one, tick. And to me, at least I'm showing some workings there. So if I've made an error, if I've got something in the wrong order, at least I'm showing the examiners that I do roughly know what I'm doing or what I'm supposed to be doing. So I would advise something along those lines, like that. And this has gone through in the books and so on, so yeah. Okay. You also then just work out the minimum weight by adding up the sides. Here's an example of how it might look in a more examination-y style question. There are some questions on the NESA website in terms of the sample HSC questions. You can have a look at some of those. And you've got a copy of this PowerPoint, so you can do this at home in your own time. And email me if you want to know the answers. Okay, so that is Standard 2 in a nutshell. Now, I'm more than happy for people to ask me questions as we go along. Has anyone got any questions about Standard 2 at all? No? In that case, we'll move on to Advanced. So, just briefly, this is roughly the philosophy of Cambridge in terms of the Advanced and indeed the extensions. Trying to maintain the current order as much as possible to avoid, I mean, look, the current order was thought up over a long period of time and we're pretty sure that it works quite well, so why mess with it? Separate advanced and extension 1 chapters so that we can distinguish between the two, and scope and sequence to help people who have the classes separately and so on. As different schools timetable differently. Building on the familiarity with the old syllabus, and I'll talk more about that as we go through. And this bit is really important. So this review of earlier work. Now I don't know how much you've looked at the syllabuses, but there is definitely a feeling that a lot of the Stage 5 review stuff has been basically taken out. So what they've done is, if you look at the subtopics and the way they're described, in a couple of places there, it says, you know, teachers may wish to review some Stage 5 material while they're teaching this topic. Yes, we may. So Cambridge have put that in for you to help you see where we think that that makes sense. And that actually you do need to do this to be able to do this. And if you've got a great class, then you can skip over that bit. But it's there because it's important to make sure that we're all in a strong place when we're starting off with the building blocks here. And if you look at the start of the syllabus, there's a page there called Building on Stage 5, and that start of the syllabus page now specifies the different topics from Stage 5 that they are saying is assumed knowledge for what we're doing. And with advanced, it's all of them except the optional topics. And with Extension 1, it includes the optional topics, even your circle theorems and so on. So that's something to think about in terms of where your Stage 5 planning is. So what I've done for these then, for all the topics in Advanced Extension 1 and Extension 2, is I've gone through and I've said, right, well, let's look at this topic, what items have been removed, what's important to just sort of flag in our brains that I need to pay attention to this, and what's new. So starting with Year 11, functions, factorisation of sum and difference of cubes has gone. In fact, if you look at how they talk about cubic graphs, they give those graphs already factored at that point in the syllabus. We don't talk about directrix, the locus of the parabola anymore, so we don't have any of that focal length or any of that conversation. That has gone. And shading inequality regions has also gone, which is a little bit of an issue if you've got any students going on to Extension 2 complex number work. It is mentioned briefly in Year 12 functions, but it's important to put those sorts of groundworks in place, and that's what you're getting from the sort of the Cambridge textbooks, is that expertise of knowing, especially with those students, where are we aiming for and what has to be in place as we go. Distance between 2 points formula isn't specifically there, but it is implied. And why it's implied is because in an awful lot of these places they say applications included but not limited to ... And of course in those places there are all sorts of things that could be hiding that we need to be really careful about. And that's one of them. Distance between 2 points could easily be in there, isn't it? Application of Pythagoras and so on. Points of note, y equals mx plus c, not b. I like that, I have to say, sorry, but then I'm English. I mean, it matches with the integration constants, doesn't it? Y equals ax squared plus bx plus c. You know, I have to have a discussion about why it isn't b. Although arguably then we should be y equals bx plus c, not mx plus b. Anyway, let's not get into that. It's not a big deal. It's going to be more of a big deal for us than it is for them. Although it'd be nice to see if they're actually going to change that in the Stage 5 syllabuses, if that's the case. Personally, if I was, going back to Stage 5, I'd start calling it that from day dot, from now on, because otherwise you're just going to confuse them and me. So as we said, we already said about the basic cubic equations. Equations reducible to quadratics aren't mentioned as a dot point in the syllabus anymore. They were, but they're not now. But again, it's an application, isn't it? So, it could be there. So we need to think about it. Midpoint formula. It's not mentioned anymore, but it's in Stage 5. That's assumed knowledge. Link to the sum and the products of roots of quadratics. You might want to put that in there leading into extension work, but it is not mentioned anymore as something that's needed. And much more focus on practical stuff rather than geometrical stuff. New things, interval notation. Do you know what interval notation is? Yes, people doing this at me, yes. So instead of writing this, we write this. Okay, gone through. It's not hard, but it's another thing of notation to do, to throw in with everything else that you're trying to show them at the same time. So we've thought, actually, that can come in Year 12, because we don't need it at this point, and we've already set them up in a certain way. The emphasis, the vertical and horizontal line test, talking about functions as one-to-one, many-to-one, one-to-many, many-to-many, and that idea of we're moving from this set of points to that set of points is focused much more. And finding domain and range of product and quotients of functions and their composites. So getting a bit more complicated there about let's look at the domain and let's look at the range. So we've got to really be careful how we set them up with the whole functions thing. Because we're going quite complex quite early, and even more so in extension 1, as you'll see. Then we've got trigonometric functions. So plane geometry has essentially vanished, haven't we? All say, oh look, there's no geometry. Except, are we sure about that? You know, so again, including but not limited to these applications, trigonometry problems, triangles, you know, there could be some things hidden in there. And when we get to extension 1 and 2 vectors, it says there could be plane geometry proofs using vectors. So we can't just write plane geometry out of the syllabus and out of stage 5. It needs to be there somehow, but perhaps lesser than it was. So we've made a coordinate plane chapter to just go over some of those basics and make sure that it is there in some sense, and that if it is dropped in various places and applications, we have got those skills. And of course, it's great setting up proofs and how you write out a proper proof. Sine and cos rules aren't, proofs aren't mentioned. I suppose they could be there as a question, but less of an emphasis on the actual proof. In fact, generally throughout the syllabus, there seems to be less emphasis on the idea of any sort of rigorous proofs. Previously, we had radians not met until year 12. They are now here at this point when you introduce them, which means you can do things like this, which is quite cool. And you can do both these things at once. So that's good. The main problem I can see with this is which mode your calculator's in. I can see that being a disaster if we're not careful, and we're really going to have to educate the students in how to do that. Speaking as someone who did their own GCSE trial exam with the calculator in the wrong mode. So I feel their pain. It can be a real problem. We won't get too many questions right, but it's just annoying, isn't it? So that's something to watch. But it does mean that all of this stuff, equation solving, graph drawing, etc., you do it with radians, you do it with degrees. True and compass bearings have now come in explicitly. And again, I'm not sure why. It just means, you know, instead of just doing the 3-figure bearing, we've also got north by so many degrees west. And so it's just about, you know, 2 different ways of saying it. It's there, it's another way of playing around with it. There's a big emphasis on the ambiguous case of the sine rule. And the reason for that is that's a distinction between that and standard 2. So in standard 2 there is no ambiguous case of the sine rule, and in advanced there is. So it's a distinguishing factor between something that's seen as common content. So you could see an exam question where you've got part A, B, C, and then part A, B, C, and D is to do with the ambiguous case over here, for example. So just about making sure you do cover that efficiently. And then this is interesting. 3-dimensional trig is now very much back in there. And I said there, the famous Uluru problem, I don't know, it's 1994 or something, I think, was it 1993? The horrible last question that was seen as the most difficult 3-dimensional trigonometry question ever. Look it up, it's fun. But it's, you know, people looking from here, there, and there, and some very complicated algebra. That's now fair game if you've got 3-dimensional trig in there. So then we come on to calculus. The structure of calculus has changed quite a lot here. So basically in year 11, you're doing your differentiation with power functions. We do a little bit of the product and the quotient rule and the chain rule, but we're going to have to do it again in year 12 because it's not till year 12 that you do differentiation with the other functions. Then also in year 12 you do other stuff in the integration and so on. So all we've got here is just differentiation, power functions pretty much. Limits are only treated very informally and lightly. We don't do limits rigorously anymore. It's more like, you know, I'll just wonder about what happens over there somewhere. But you know, maybe that's okay for advanced level students, but it's a bit tricky when you're setting up the ones for later on and being rigorous again. It's less of a focus on the whole geometry idea. It's much more this rate of change idea. Instantaneous and average rate of change, which is no bad thing. So we've got some rates of change, talking about things in context. What does that mean, this changing with respect to that? Which is, after all, how calculus then comes into the real world, isn't it? It's not just all about graphs, but an understanding of graphs is very helpful. There is some of that there, but just less of an emphasis on the geometry. So geometrical interpretation is still there, but just less so. Motion is an interesting one. Motion is only mentioned as an including but not limited to motion in a straight line. So it's not a separate topic, but it is there, so it needs to be covered. Here's some possible practical type problems. We've seen these before when we're doing rates of change. Perhaps haven't seen it at this point in the proceedings. We've seen it more when we do rates of change as a topic later on, but this sort of stuff. And then you've got the exponential and logarithmic functions comes immediately after that in the syllabus. Now, what Cambridge have done is we've said, well, hold on, if we're doing power functions, don't we need to have gone over index laws? You know, you need to know about indices and how that might play out and so on. So there's a small chapter before the calculus that goes through the index and log laws, and then afterwards you come and you meet the natural log, and just made that natural distinction because it makes much more sense in terms of a flow of learning. The reason they've put this here afterwards is because they'd like you to discover E. And actually, it's a fun activity if you've never done it. So you go on Desmos or something and you put in the graph of a to the x, then you put in the derivative graph, and you play around with the constant controller and show that they sit on top of each other when a is E. And it's a nice activity to do. It could even be an investigation. So you zoom in and you find, look, A is 2.71, etc. But, as I say, in terms of the rigour as well, that needs to be in there as well, and understanding that. But there's so much more. It's not emphasised through first principles anymore. It's more just about understanding the reason E is useful is because when you derive it, you get itself. What else have we got in here? We've got the whole emphasis. In fact, I think it even says using technology in the syllabus. So it's important to do at least some technology there. Emphasis on the practical aspects. Where are logarithms and logarithmic scales used? So the Richter scale, the fact that Australian banknotes are based on a logarithmic scale. Lots of investigations could come in there. In the textbooks, there's an idea for a project on logarithmic regression and other things like that. So lots of ideas here for actually how do we make this applicable, and let's look at that in a bit more detail. And then the last topic of Year 11 is your statistics. So statistics here, common content with Standard 2. Nothing's been removed because there wasn't anything there before. So this is new for these people, new for some of us. It does mean Stage 5 statistics might now have more importance. Stage 5 statistics and probability maybe. I mean, there was probability up there, wasn't there? But not so much. It sometimes ended up being a sort of end of the year topic. If I have time, I might. Now probably needs to refocus in importance on covering that statistics. So the probability is pretty much what was there before, but we've now also got conditional probability, which was not there before. So conditional probability is new, more of an emphasis on Venn diagrams and set language. Random variables and then discrete probability distributions come in as well, and the whole idea of sample and population mean. And something we haven't seen before, but which they've been doing in other jurisdictions for a while, simulations and trials. So the idea of using the random number button on the calculator to generate random numbers, and then saying, okay, if I want it to be, I'm picking something out of 10 things over here, let me use the random number generator to show how that might happen. It's the same probability, whichever thing I'm doing. I don't know how complicated that'll get, but we've thought about that quite at length. This sort of thing we've seen before, probably focusing more on the complicated ones where we don't know the middle bit here, and then we've got to express everything else in terms of x and work out what x would be. And conditional probability questions such as this. So that's about knowing these probability formulae and knowing them in terms of the Venn diagram. I could see some nice activities with shading in Venn diagrams. Which bit do I mean by this bit and which bit do I mean by this expression and so on. And then when we come to discrete random variables, it's so important to get the notation set up correctly from start. There's been a lot of toing and froing to try and work out from our point of view what is correct from a university point of view, from a mathematical point of view. Where are we with this notation? I'm talking about little things like, you know, a little x or a big X, and where does it come, and do we really understand exactly what we mean by that? The actual mathematics itself isn't that hard. I mean, we know this, don't we? You know, if I throw a coin rather 3 times, what's the probability I get no heads, 1 head, 2 heads, 3 heads? We know those numbers, that's okay. It's about how do we set it up so we can then later on build on that and have expected value formulae, variance formulae, and so on and so forth. As especially, this is discrete, 0, 1, 2, 3. What about when it's continuous, which becomes more complicated? We'll look at that in a minute in Year 12. So getting the right resources, etc., to make sure that all that notation is spot on and you're delivering that accurately and properly is really important. So then we go on to year 12. And year 12 kicks off with two topics put in together, advanced functions and trig functions. And they're both basically doing the same thing. You've got advanced functions doing, take all these functions and transform some graphs with them. And then you've got trig saying, take these graphs and transform them like this. So it's basically the same thing. So let's put them together and just do all the functions. Makes much more sense, doesn't it? We've previously not had more than two transformations at once, but we can now have as many as you like. So you can see, we can see something happening along the lines of this, something like that. You know, how does that transform the squared graph? And of course, there's a nice link there with completing the square and so on. I can see lots of work on Desmos in this and moving the constant controllers around. Nice investigations happening here. The order becomes so important in terms of that, and that's even mentioned in the syllabus in terms of the order of that. I don't know if I've got that on that slide or if it's the next slide. Yes, here, care is needed around the order. So this sort of thing would be very useful. You know how when you get them drawing graphs, you have a sort of graph sketching menu in your head. Like, what are the things I need to do when I'm drawing a graph? I need to do this, then this, then this, then this, then this. So that sort of idea of, okay, so I want to say, right, what's happened to the x from the x squared? What's been replaced by what, and where's it happened, and how has it become what it now is? In what order? And because they talk about the order, I could see questions along the lines of part A, do these transformations in this order. Part B, do them in this order. What's the difference between them? How would I then get from that one to that one? And so on. And some nice things with fitting curves to things. You know, if I can move them around wherever I want, I could do some nice fitting of them, couldn't I? So then we've got calculus, and this is huge in year 12. So we've got all the differentiation for all the other functions. We've got second differentials and everything that involves. And we've also got all the integration. Although not volumes of solids of revolution, because they've gone to extension 1, they're not there anymore. This approximation of sine and cos isn't explicitly mentioned, and neither are Newton's laws, but could be implied. I say volume of solid revolution has gone, and so has Simpson's rule. So you've only got the trapezium rule now. So Simpson's rule's out, gone. Things of note, a little bit of notation and language. We're now saying ln x, which sort of makes sense for the calculator, doesn't it? It's less confusing on the calculator for them. Inflection, not inflexion, for whatever reason. And we're saying antiderivative, not primitive. And the fundamental theorem of calculus is mentioned, but not mentioned anywhere near as much as it used to be, and so it's very much a bit like the whole doing things from first principles. We mention it briefly, but we're not going to get too bogged down in it. And lots of other applications, not just time. And one thing it talks about is that, unfortunately, this sort of stuff comes back, increasing at a decreasing rate, and all that stuff that people get very upset about on things like the Mansfield Facebook page. You know, increasing at a decreasing rate, which graph does that, and when it does this and this, and which way does it go? I mean, thinking about it in a particular application always helps. So house prices increasing, but not as fast as they were. How does that look on a graph? Thinking about that more, and also just more optimization problems, not just geometry. Here's a more sophisticated one for you, so making it a bit more complicated. Then we go on to finance. There's no sigma notation. So no sigma notation, although we're about to do geometric series and arithmetic series, no sigma notation. There's no sigma notation in extension 1 either. So yeah. I think you'll find that it has been dropped into various points in the textbooks, and you could choose to ignore that bit or not, but you know, how are you going to talk about this in a very logical, concise way without some form of sigma notation? And it's not a hard thing to teach them, is it? So why it's been removed, who knows? The limit's not treated formally. So again, we're just talking about that, and it's not been treated formally at all, has it? So what we've got here in this section actually is it's 4 parts. The first part is the part that is common with standard 2. So tables of future value interest factors and that stuff, and your compound interest. Part 2 is arithmetic sequences and series. Part 3 is geometric sequences and series. And the last part is then putting that together in your applications of series in annuities and so on, as we're used to. So the last three parts of those is what we've had before. The extra bit is actually the simpler stuff, the standard 2 bit. And then what it adds at the bottom is using your sequences and series to explain things like where do the numbers on the future value interest table come from. So actually trying to then link that back in some way. So a bit more of the application side of that. So using that for checking values. But there's a lot of common content here. And of course, compound interest hasn't been covered separately. It's assumed knowledge from stage 5. But they're generally all okay-ish on that. And then we come to the statistical analysis, the last topic in year 12. So a lot of the first part of this is already in stage 5. That's your bivariate data. And considering these are now the students that should have been doing all of 5.3, hopefully you've covered quite a bit of that, but you might need to revisit and see. Pareto charts are in there. And we've got the outlier definition being quite precise about the 1.5 times standard deviations. But we're also told that that will only be in some contexts. So of course, if you've got a short list of numbers, it's not appropriate to do that. It'll only be some contexts. Very much an emphasis on the statistical investigation process. So how they're going to examine that, I'm not sure. It would be a good investigation, funnily enough. But I could see some more wordy problems. If you look at some of the things that were produced for the standard 2 sample questions, you've got things like, this question, why is this question biased? Give 2 reasons, which we used to hate in the UK, but hey, we seem to now have it here. And also this is nice, making a link between the integral, the area under the curve, and the probability distribution. What I mean by that is this. So here is my value A, and here is my value B, and here is my graph of the probability density function. Then the probability of the value being between A and B is the area under that graph. And so that's a nice link there with the area under the curve. Because we've taken away volumes of solids of integration, we've got this instead as a different application, different type of application. And then, of course, with the normal distribution and the empirical rule and how much percentage of here, which we've had at standard 2 before, but haven't had here. But again, a link with the area under the graph there, which is quite nice. So that's advanced. Any questions on advanced? Okay, I'm sorry I'm having to go so fast. It's just there's not much time and so on. I'll try and keep people awake. I know it's the end of the day. Right, extension 1. So we start off extension 1 with functions. We've lost iterative methods for functions. They've gone. What actually is here, and some people look at this and have a sort of panic attack, because what it looks like at first glance is all the extension 2 graph sketching material has come here. And it looks pretty scary when you think of it that way, but I'm not sure it's meant to be quite that nasty. No methods are talked about doing the really fancy graphing. It's much more about this curve plus this curve, what will that look like, but without doing all your fractions work and so on. So it could be as simple as, right, so this graph's here and this graph's here. Well, that plus that is that plus that is that. Plot the points, join the dots. So it could be as simple as that sort of thing that they're really talking about here. You've got inverse functions and parametric equations are here. And one of the problems here is with the programming, so using the textbook advice for programming, because what we're talking about here is doing some quite complicated algebra at the start of year 11, potentially. Is that the best time to be doing that, really? Especially when, in the advanced course, we're just doing, cubics without even factorizing them. And then here we're doing this sort of stuff. So the timeline needs to be thought about really carefully there. As I say, there are scope and sequences in there. We've got the quadratic inequalities and absolute values have moved here, and multiplicity of roots from extension 2 has also moved here. Okay. And this is the sort of thing you might have. Here's some parametric equations. Show it's the equation of a circle, for Cartesian equation of a circle, for example. Then we've got this. Now what's here is just simply sums and differences, using products as sums and differences, but there's an extra word that wasn't there before, which is the word derive. So we're asked to not just use the products as sums and differences, but to actually derive those formulae. So do they mean something like this, where you've got your points P and A on your unit circle, and then you've got your D squared using Pythagoras, use the cos rule, and then we equate them. It gets a bit nasty, doesn't it? So you've got all this there. I'm not expecting you to follow it precisely, but you get these formulae, and then you play around with them, and that's where the equations come from. One would hope they don't imagine the students to be coming up with that off the top of their head. Hopefully it would be a little bit staged along the way and helped, but it does say derive there. So that's something to think about. Then we've got the extension calculus. So what's here is all the exponential growth and decay. So exponential growth and decay is no longer in advanced, it's all here, both the basic and the modified. So it's all there in one hit at this point. And some of the Newton's laws has moved there, including but not limited to applications such as motion in a straight line, Newton's laws, etc. Here's an example of how that might look, more of a wordy problem. So not just looking at the graphs, but this isn't anything that we're too unfamiliar with. We've done ones like that before in the current syllabus. Then we have the last topic of Year 11 in Extension 1 is combinatorics. So this is permutations and combinations, mostly. And then the random half topic shoved in of the polynomial theorem. Because actually if you're going to use the permutations and combinations things, you need to know the polynomial theorem. So it's sort of been almost put in there as an afterthought, but anyway, it's there. It's not clear quite how detailed they want you to go on this, but it is clear that we don't have anywhere near as much emphasis on the further properties of the coefficients, and that greatest and least coefficients and terms are gone. So we don't need to worry about that side of it, but it does talk about combinatorial proofs. It gives one example in the syllabus. One would hope that eventually this topic guidance will give us more information about that, but we've done quite a lot of thinking about that and thinking about where it needs to come. And then you've randomly got the pigeonhole principle is popped in there as well. Mostly I think because it's in Akara, so it's here. And we're just talking about things like this, pulling socks out of drawers in darkened rooms and that sort of stuff. So good real life stuff. I like that definition of the pigeonhole principle personally, drilling holes in pigeons. Appeals to the mathematician's sense of humour. So then Year 12, we start off Year 12 with proof. This is simply the proof by induction. And in fact, it's only half of proof by induction. So the old proof by induction topic has been taken, and all the hard stuff, like geometrical ones or inequality ones or things like that, and anything where the basis case is not n equals 1, is in extension 2. So this is just your easy, basic, bod standard, do a proof by induction. What it does have extra is that you need to be able to identify errors in existing proofs. So something like this. If I was trying to do this proof, show the inductive step works, but the basis case doesn't, for example. Or it could be, here's a proof, what's wrong with it? Maybe. Then we come on to a new topic, vectors. So how many people have done any vectors? More than before. So some people maybe at university or when, or yeah. So vectors in the UK is actually, it's done at GCSE level, so Year 10 level, so it is there, and there's probably quite a lot of resources online from that. However, we've got things here like doing projectiles with vectors. Now, we've always sort of done that because you've done the vertical and you've done the horizontal separately, so it's just really a question of how do I write that at the end? Do I write it as a something I plus something j, whereas before I'd just written them separately. So that's not too worrying about that, but it does mean that projectiles are here. This bit is a concerning bit about plane geometry, because there's a dot point there saying geometrical proofs using vectors, and I'll show you one in a minute as to what we think. One thing I would definitely say is that if you've got students that are doing extension 2 and extension 1, you should really be doing the extension 2 vectors and the extension 1 vectors at the same time, because this is basically do all this in 2 dimensions, and then extension 2 is now do it in 3 dimensions. So they're very, very linked. And it would make sense to sort of build one on top of the other like that, if possible, if your timetable works that way. So nearly all of this topic is new. Let's have a look. One thing you want to try and get clear to them from the start, and maybe even further down at school, is the difference between a displacement vector and a position vector. So a displacement vector is this idea that here is my vector, it's going this way like this, and I can pick this up and I can put it wherever I want. I can put it here, I can put it here, I can put it here, wherever. It's just a direction, basically, like a gradient. And then a position vector is from a particular point, the origin there, to here. So it's locked in place. And then when you're going on to find equation of a straight line later on, you're going to link those two things together. So getting that distinction is really important at the start. And also we've got this idea of here's one vector, here's another vector, and if I have u plus v, I've got a parallelogram, and the one down the middle is the u plus v. So we've got parallelograms, we're already thinking geometry stuff going on here. Here's a geometric proof. So the dot product, which they don't have the cross product. Anyone who does know about vectors, don't go as far as the cross product, but oh well. The dot product basically says that if I dot two vectors together, and there's a way of doing that that's a clever way using the different parts of it, it's the same as the length times the cos of the angle between them. So if I have something like this, prove that the angle in a semicircle is a right angle. Oh, circle theorems. I thought they'd gone. They're in stage 5.3, aren't they, as an optional topic? Who's to say they might not be there somewhere, although arguably I don't have to remember it, I've just got to prove something about it. So if we can remember, we were back here, and we said dot times length times cos the angle between them. So if I just simply dot things together like this, a dot a, then I'm just going to get the length squared. So if I do this one minus this one, I get 0, and I can treat this, and that's something else that you learn, as though it was just c squared plus 8 minus a squared, so it's a difference of 2 squares, and I can write it like this. So those two things dotted together is naught. Now if two things dotted together are naught, that implies that they are perpendicular by the fact that the definition of what it is. And if you look here, this is c plus a, and this is c minus b, and of course if a is minus b, then that means that that is c minus b. So dotted together they're perpendicular, and there's a proof. Now, are they really going to expect students to come up with this sort of thing? I don't know. But the book certainly goes through some elements like this. Here's a much easier one, which is like the sort of thing that you get them doing in year 10 in the UK. So here is a triangle. This is x, this is y in terms of vectors. So we'd say MA, well, we're told at the start the ratio of these sides, or that this one is a fraction of that one. So MA, we can say that as a fraction of x. I can say AB. To get from A to B, I do minus x plus y. So AN is a fraction of minus x plus y. And then MN is that fraction of x plus that fraction of x minus y, minus x plus y. And you get an expression for MN. And you should find that that expression for MN is a multiple of the y. And if one vector is a multiple of the other one, they are parallel. So I can show that they're parallel that way. And these sorts of questions are done a lot in the GCSE in the UK, this type of thing. So I can see it probably being more like that than like this, but it's good to throw in some of those as sort of extension work, because you never know whether you might have something difficult at the end of the paper. Then we've got the trigonometric functions in year 12, and they're basically just the whole business of I've got a sine function plus a cos function is r cos theta plus alpha. We've done that before, we know that one. Using Desmos, we might want to show, because it does say using technology, that if I add two trig functions together, I get another trig function. But otherwise, that's not anything we haven't done before there. Here's a more complicated example for you to peruse at your leisure. And then we've got calculus. So still, no sigma notation. So there's no sigma notation still, so we're still dealing without that. The limit is still not treated formally, but here are my volumes of solids of revolution. They're here at this point. And I've also got these things: first order differential equations, direction fields, and the logistic equation. Do you know what direction fields are? No? They look like this. This is a direction field. So here is an example of a question. So here is my differential equation, this. I know that y dashed is always minus 2xy, so at this particular point I can work out the slope will have gradient 2. I then do that for all the other points, and then I can get the graphs that might represent that differential equation by basically joining the dots like that. Now again, I'm not sure how they examine that, but I could see a great multiple choice question there Here's the differential equation, which of these direction fields fits it? That would be a nice multiple choice question, for example, wouldn't it? Then we've got statistical analysis at the end there. So we've got the Bernoulli and the binomial distribution, and this is the topic as far as we go with statistics. There's none in extension 2. Bernoulli and binomial and approximation to a normal. The second part of this is a very, very small topic. It's only about 2 dot points, so that could be something that's just done an investigation. But basically you need to get the idea that a Bernoulli trial is something where it's either a success or a failure. So it either happens or it doesn't happen. So you've got a 0 for when it doesn't happen, a 1 for when it does happen, and the 2 probabilities add up to 1. And that means we can have expected values and variance using various formulae this way. And then binomial is when I do lots of Bernoullis. So if I've got a thing that I do, and it's either a success or a failure, I'm then going to do that lots. How many successes am I going to have if I do it lots? How many failures am I going to have if I do it lots? And there are various formulae involved in that. Here's a sort of question. So if I'm doing a multiple choice, for example, and I haven't revised for it and I'm just guessing, what's the probability I'm going to pass the quiz based on the expected value that I'm expected to get? Then the normal approximation is basically the idea that if I do lots and lots and lots and lots of Bernoullis, like a huge number of them, then I can actually approximate that. Instead of using the binomial, I can say, well, it's roughly turning into the bell curve when it gets really, really big. So that would be a nice investigation, especially using some technology to show the more I do this, the more it looks like the bell curve. And if it gets really big, then there's various formulae I can use to change from the binomial distribution to the normal distribution and use that approximation. Okay, extension 2 then. So there are only 5 topics in extension 2. First topic, proof. So we've got the other half of the proof by induction, the harder stuff. So the stuff with geometry, the stuff where the basis case is bigger than 1 or the steps aren't consecutive, slightly nastier, more complicated proof by induction. And we've also got some new things of proof where we're using this sort of stuff, where we're using the if and only if, for all, there exists, and so on. Proof by contradiction, using the logic language, and so on. We're also allowed sigma notation, hooray! So we can now start using sigma notation at this point as well. Here's a proof by contradiction. I mean, roughly the idea is, here's a thing I want to prove. I'm going to assume it's not true and show that that makes no sense at all, basically. So that's the way it works. We could have a geometric proof by induction. This one's actually taken out from one of the current Cambridge books. The idea that you've got a plane with some lines in it, and if I add more lines, that adds how many more regions, and there's a formula for that, and we do it by a proof by induction. So you could have those that aren't just simply the algebra. We have vectors. So vectors is doing everything we did in extension 1 in 3 dimensions, and also adds the idea of the vector equation of a straight line and makes the link with parametric equations, so writing equations in Cartesian form as well. I need to get the idea between my axes, and maybe it might be worth going back and thinking about plopping some 3D coordinate activities in maybe study year 10 somewhere, or end of year 9 or something like that. And this idea of discussing the planes as x, y, x, z or y, z, again, you can drip feed that in lower down the school with the idea of drawing a bird's eye view and an elevation view of things. Just actually maybe that becomes a bit more important if they're going to need to be able to think like this higher up the school. The reason we've got vectors in 3 dimensions, in fact the reason we've got vectors full stop, is the idea that gradient doesn't carry into 3 dimensions. So how do you talk about the direction of a line in 3 dimensions? You can't, unless you've got vectors. And that's how you talk about the direction of a line. And of course the other idea, and I say that I keep meaning to put this right in, I still haven't, lines which are not parallels, you might want to add the word not there, that's a misprint, my fault, sorry. Lines which are not parallel may or may not meet. So on the 2-dimensional plane, if lines aren't parallel, they're going to meet, right? But on the 3-dimensional world, here's a line, here's another line that's not parallel to it, they're not going to meet at all. You end up doing this a lot when you're doing vectors. I get straws, actually. Really good tip. Use straws and have straws to sort of talk about this and imagine the straws like lightsabers with beams coming out the end and how that looks when you're talking about vectors. So this is the vector equation of a straight line. this puts together that idea I said earlier about position vector. So this is a position vector. Here's the origin. Here's my position vector to get to A. And then I add that to this direction vector. So you can see that's very linked to the whole point gradient form of equation of a straight line. So you can make that link, and you could even do a little mini investigation about that. We get to the line, and then we have some multiple of that line in order to get to any point on the line. And here's a sort of example. Usually we use lambda. That's what's been used before. The idea, if you've got, here's my position vector, and here's my direction vector. Find a vector equation for the line through that, parallel to that line. Complex numbers. We're on familiar territory here, mostly. Except we've got this, Euler's formula. So Euler's formula is hooray! I like Euler's formula. When I first arrived in Australia, I was actually given an extension 2 paper to work by someone at my school. And I did the nth roots of unity using Euler's formula and got told off for it because I'm not allowed to use Euler's formula, but now I am, so it's all good. It's so much easier when you're doing it that way. So Euler's formula is the whole e to the I theta. Now, that does mean, however, unless you're just going to say, here's a magic formula that just works, well done, everybody, here you are, use this. It's a good idea to explain where it has come from, even though I'm not suggesting we start teaching Maclaurin series, because that's complicated. But cos can be expressed in this way, sine can be expressed in this way. So e to the I theta, because we know about this, can be expressed in this way, and then we've got that this is true. And of course, this does mean that when it comes to Pi Day and we're all walking around wearing t-shirts that say this, they'll know what we're talking about. It's great. If you happen to be the sort of maths teacher that likes doing that. Arguably the 5 most important numbers in maths ever linked in an equation, which is quite exciting. So we've got that there. Otherwise, it's pretty much what it was before. You've got regions of the complex plane, might be some locus work, but be aware, so we haven't, remember, from earlier on, unless you've put it in there through your resources and so on, you haven't got any shading regions and you haven't got any locus work to build that on. So you're going to teach it all at that point? Well, maybe that's an option. There's arguably less content in Extension 2 now, but maybe it's also a good idea to put that in earlier on. Calculus. Essentially here you've just got your partial fractions and you've got integration by substitution. There was some integration by substitution in Extension 1, given the substitution. Here, it's integration by substitution without being given the substitution. So you're going to have to think about, how am I going to train the students to know the sorts of things to try? And something like this would be a good idea. So, if this, try this. If this, try this. This whole idea of, look, I don't know what to do, but let's try some things and see what happens. Then mechanics is how we finish off. So circular motion has gone. So we may or may not be happy about that, depending on the context. But what's gone in there is this, projectile motion under resisted motion. If you look where that is in a lot of other places, that's second-year university physics. So goodness only knows why it's in there, but it is. In there it is. What it means is basically that you've got your projectile flying like this, and at any given moment in time, you've got the air resistance acting directly against it in the direct opposite to it. So you're going to have your vector different components and what's happening at any one point using all the resisted motion you've just taught them. It could get really nasty. So again, really important we set that up correctly. That's it. Right.